So on behalf of Jen, Kano, and myself, I would like to welcome everyone to here to participate in this program. Obviously, we want to thank KITP for putting this one-day teachers conference together, but also to allow us, myself, to be here for 12 weeks, coming from Houston. It's a real treat. And also, I want to mention that my daughter is in high school, senior, taking physics for the past few years, and physics is one of her favorite subjects, if not the favorite subject. So I'm grateful for everybody's contribution to the next generation. The program today has a title, What's in a Crystal? And we want to convince you that the first thing that should come to your mind when you think about a crystal is a quantum universe. And so that's what we're aiming for today. And so I'm Qimiao from Rice University. I do want to thank the funding from various federal agencies and foundations that allows me to work in this area. And so, we are condensed matter physicists. And so at some dinner gatherings, people would ask me, what do you do? I say, I do condensed matter physics, and different kind of reactions sort of ensue. But the one way to characterize what the condensed matter physicists do is about the organizing principles that underlie things which are, some of them are actually very familiar to us in daily lives, phases of matter. And so ice, water, vapor, these are things that we encounter on a daily basis, and they all are made of H2O molecules, and depending on the condition that this bunch of H2O molecules are put under, they organize by themselves into different forms, right? So that's really the essence of condensed matter physics, the form of matter, and then we delve deeper into it, the excitations that also exist depending on the form that they organize. Now, going sort of to a larger scale, if you stare at the sky, probably the phase of matter is not the first thing that would come to one's mind. But in fact, phase of matter also operates under, for the objects that we are staring at, there's a neutron star and all the other wonderful things that exist in the universe. And physicists spend a lot of time, effort, and also resources to study the questions which are relevant to such objects. And so you heat it up or changing the conditions. And these are the theoretically predicted phase diagram that maps out the different kinds organizations, in this case, quark and other things that come with the quarks. So that's again the issue about organization of a large aggregate of microscopic particles, in this case, quarks and gluons. Now, zooming down to what we are talking about today, we are talking about electrons in a crystal, any characteristic crystal. And the first thing that one should keep in mind with electrons in a crystal is that there's an extremely large number of them. And so, so there's a famous saying by the astronomer Carl Sagan, and the statement was that there are more stars in the universe than there are sands on all the beaches on Earth. There are more stars no, but there are more stars, I'm coming to that, but there are more stars than there are sands on all the beaches on Earth. I think that's what Carl Sagan said. So playing on that theme, a variation of that theme is that there are more electrons in a single grain of sand than there are stars in the universe. So that's the kind of picture that we should keep in mind when we deal with numbers like 10 to the 23. Okay, and it's a huge number. So we physicists, condensed matter physicists call such things as very generic name many-body system. So the many here is a huge number. So that's very important for the electrons in a crystal. And the other thing that one should keep in mind is that an electron is a charged object. So in physics, we know charged objects, there's a Coulomb electrostatic force, E squared over R, and in a medium, there's some variation of it. And so the typical, when you have so many electrons in a piece of crystal or a piece of solid, the average distance between the electrons is very small. It's atomic scale, angstroms, right? So you put in the number E and put in, and calculate E squared over R, that comes out to be several electron volts. So what does that mean? If we convert into the scales that we are familiar with, so I'm from Houston, our room temperature in Houston is somewhat higher than room temperature here, but nonetheless, the room temperature pretty much everywhere is on the order of 300 Kelvin. 300 Kelvin, if you put the Boltzmann constant and other things, converts to about 25 milli-electron volts. And so electron volt is like 40 times of the scale that's relevant to condensed matter physics, right? So that's a huge electrostatic interaction potential. And so we'll come to that as well. And so we want to give you the sense that the quantum universe is what's going on for the electrons in a crystal. So let's start from the classical world. Classical world, Newton told us that F is ma, that if I have a particle of mass m, and if it's moving, say, in one dimension, in an environment that provides a potential V for the particle, we can determine what the force is, and then we can follow where the particle is moving to, knowing the initial condition, right? So that is the classical world. Well, electrons don't act as in a quantum mechanical way. So Schrödinger said that the potential doesn't just come in as a force and come into F equal to ma. The potential shows up in the Schrödinger equation, which determines this object psi. That's the wave function, okay? And so the wave function depends on position, depends on time, but this is a very deterministic equation that will tell us about the evolution of this object, this wave function. So that there's an equation to be written down, it's deterministic, right? But the outcome of the wave function, and this wave function is what's showing up in the logo of this conference, the wave. It tells us a number of different things. It tells about the probability distribution of where to find this particle. And I couldn't resist putting on this figure, which is from the book by Griffiths and Shorter, because my daughter came back with a homework assignment several days ago in her math class, actually. So I think we have some math teachers in the mix here. Not a whole lot, but there's several. So the assignment was to play with this probability distribution, right? So this follows from this wave function. But the wave function, the probability is actually the modular of the wave function squared. So we only care about amplitude. But this is a complex function, so it also has a phase. And this phase will play an extremely important role for today's program because it leads to topology, as you'll see the very detailed discussion that will follow. So coming to the quantum universe, we have many electrons. Each electron is a quantum mechanical object that qualifies as this aggregate as a quantum universe. But there's also interaction. I try to impress upon you that this is a very large scale. So again, coming from Houston, I know what the traffic jam is. These are in many ways interacting, an aggregate of interacting particles, and they can get stuck as a result of interactions. And that also will come in today's program. And so it was already mentioned by Mark that some of us have already been here for 2 weeks already, and we're going to be staying here for another 10 weeks. So that's a 12-week program that plays on the theme with very detailed exposition of various objects, topics. And so don't worry, I'm not going to get into each of these details. But we also have a 4-day conference that Mark mentioned that's going to start on a Monday. And so again, will be the same theme, only 4 days, so it will be simpler than that. But you have the crystal, you have electrons which are behaving as a result of the wave nature, quantum mechanical nature of the electrons, and also as a result of the interactions that they experience. So the theme is topology, interactions, and symmetry that connects with crystal. Crystal has a very high symmetry. And so that's our quantum universe that we're going to go through today. So buckle up. Here's the tour of this universe, and we'll start in the morning on a more weekly interacting side. Will be discussed by Giancarlo Fang, who unfortunately had to cancel participation in person, but he graciously agreed to connect by Zoom, and Matt Beekman. And in the afternoon, it will be more on the effect of interactions that join the mix. So with that, I think that's my job to really to introduce this program, and I think we can get to Jen.